do my best. Today is a programming day, so open up idle if you'd like to. We're going to keep on going from where we stopped last time. Remember we were making a bouncing ball? That was cool. We're going to add to that today. All right. So I guess the first thing I want to talk about is, let's bring in the stuff from before. Let me see how I can do that in a nice way. It's on my desktop, right? This one. What lecture are we today? We're lecture 26. So let's make a folder for us. And then let's copy in the bounce from last time. I don't know. I'll call it bounce copy just to make it clear that I'm taking this from somewhere else and I don't think I'm going to change it. I'll do something in a new one today. But let's open this in idle. So this is where we were, right? We had this nice program, draw a rectangle. And we ended up with this outcome. Draw a rectangle, then forever, while true, repeatedly just draw a new frame, which dealt with moving the turtle by the offset, bouncing the turtle off the wall by changing the offsets. And we get some nice smooth animation because of it. All right, so that's where we were. And I would like to talk about that now. Why in the world does just saying while true draw frame, which says turtle.goto, why does that produce animation at all? Right? Because it's like draw frame, forever and ever and ever. How does that actually make it look like something's moving? Right? So in theory, right, if the program just kept drawing frames, it would never finish, and so it would never show anything at all. Right? That's one way you can think about it. So maybe it's just like try to start drawing your first frame with the ball up here, but then immediately start trying to draw the frame with the ball over here, and so they all just overwrite each other and then you never see anything. Why isn't that happening? Why not just show those frames so fast you'll never be able to see what's going on? So maybe it's like always clearing the screen to draw the new frame. That is not what's going on. And then there's also no concept of waiting, right? Last time I talked about frame rates. Movies, for example, are like 24 frames per second. If you want to make a movie, you have to like show a frame for 1/24th of a second, then show your next frame for another 24th of a second, then show your third frame for another 24th of a second. I never said show a frame for a certain amount of time. I never talked about time in this program. That's a little weird. That's a little fishy, okay? So the reason it's making animation is it is drawing every frame to completion, first of all, and then also it takes a while to like think about where to draw the turtle and actually like write all the pixels on the screen. So it takes a while to draw stuff on our screen. All right. So there is actually a tiny amount of time where it's drawing and that's all it's doing. It's drawing the pixels, it's moving the turtle around, it's thinking about turtle stuff. And that is what gives us animation. There's a little bit of time, like it takes a certain fraction of a second to call draw frame, put the turtle in a new spot, write the pixels on the screen. That takes a certain amount of time. We can time it with some function calls if you want to, but this is what's giving us animation. It's because like the computer is trying as fast as it can to draw a frame, but it takes some time still. All right, maybe it takes like a 60th of a second to draw a new frame, for example. And so if I just keep calling draw frame, it'll take another 60th of a second to draw that next one, even though I never talked about time anymore. It was just, it took work to put the turtle somewhere on the screen, and that work gave us a frame rate. We didn't even have to think about it, all right? If you have a faster computer, though, it's going to be able to draw faster, and so maybe the turtle on your fancy computers that are so tall, maybe it's moving faster if you run the same program. Like, it might be moving much faster than the ball on my screen because it can do more computation in a second to your fancy large computers. That's the idea, but that's why we're getting animation. All right, does that make any sense? Any questions about that? If you wanted like fine-grained control over your frame rate, over like how fast the animation was being shown to you, there is a function in the time library. If you import time, it's called time.sleep. I'll show you that. Python time. Let's see here. Sleep. Time.sleep, and then you give it a number of seconds or a fractional number of seconds, and it will just stop the program. It'll wait for that many seconds. Time.sleep. All right. So technically, if you would like your frame rate to be much slower, you can like wait 1.5 seconds in between frames, for example. All right. That's the idea. So that's the secret. That's the reason we're getting a frame rate. It's because that draw frame call took some time. We didn't think about the time. We didn't like express, oh, I need 1/60th of a second in between frames for a 60 frames per second animation. No, we just let the computer do its thing, draw as fast as it could. And that gave us some amount of frame rate. Any questions about that? And of course, we noticed last time that if we changed the offset, this value, the magnitude of the offset, like if we made it -5 rather than -2, it would, for each frame, move faster each frame. So that would also affect the speed that we as humans see when it's running. It's moving more each frame. Okay, so that is animation in a nutshell. I would now like to edit this program and make it look a bit more like real life. So right now it's just bouncing up and down like it's in outer space or something. Let's make the ball bounce with gravity, because if you drop a ball in real life, even if it's a nice bouncy ball that bounces right back up, it's eventually going to stop, right? And also when you drop it, it takes a while to get to the ground, but then it starts speeding up as it gets closer to the ground, right? That's how things work in physics in real life. Then it bounces back up. It slowly starts bouncing back up, but then it gets a bit faster as it starts getting higher in its bounce. And then it goes back down and gets a bit faster as it's falling down. Whee! So there's like a... And then eventually it'll bounce enough to not bounce anymore, right? It's not a perfectly elastic collision, if that's the word that I'm remembering properly from physics. Okay, so if we want gravity, we have to have the ball do this. The ball, as it's moving downwards, it should be moving pretty slow as you first drop it. And then once it gets to the middle, it's going a bit faster, dot, dot, dot. And then the fastest that it moves is right before it hits the ground. Super fast. Super fast. All right, that's how things work in real life. Any questions about that? We all dropped a ball before, I hope. All right, so in order to do this, we have to actually model physics in our program. So what is it that's making this ball like go faster as it gets closer to the ground? It's gravity. We have to model gravity in our program now. All right. So just in case you haven't taken a physics class yet, let me teach you about kinematics. I'm going to use some words that one day you will know if you don't know them already. Right? So, all right. Right now, our ball is moving at a constant rate each frame. Like this is its offset. It's -2 or +2 once it bounces off. So it's moving by 2 each time in one direction or the other. All right? So that's constant velocity. Right? Velocity is your change in position. Velocity equals delta position. And if we have gravity, gravity affects velocity. All right? So first of all, constant velocity is not what happens in real life. That's what happens in outer space. The ball should be speeding up on its way down. And the question now is, like, how does gravity affect our velocity? Like, we drop it, it's not moving at all, but then it starts speeding up even more and more and more until it hits the ground. So gravity is affecting the velocity of the ball. All right. So how fast does a ball in real life change its speed? That's the question. And we could reformulate that question and talk about the actual physical term, right? We're asking, what is the acceleration on the ball? And that's what gravity is measured in terms of. It's an acceleration. Acceleration, remember, or I'm teaching it to you now, it's the change in your velocity. So it's how fast your velocity changes. So it's like the measure of how fast your position changes, kind of. There's two deltas involved there. All right. So in real life, at least, the ball is accelerated by gravity at 9.8 meters per second squared towards the ground. All right. And another way to say that, because there's like a squared involved, like in the denominator, like how do you interpret that? The way you can think of it is the ball speeds up by 9.8 meters per second every second. That's where the square comes in. It's affecting the velocity. So every second, if you drop the ball and it's moving 0 meters per second, the second you drop it, a second later, it's going to be moving at 9.8 meters per second. Another second later, it's going to be moving at 20.6 meters per second. Okay? That's the idea. So the ball is affected by acceleration to the ground, 9.8 meters per second squared. All right? That's the idea. So, yeah, we need to program this. We need to let acceleration, we'll pick a nice value for acceleration. It's probably not going to end up being 9.8 meters per second squared because there aren't meters in Turtle Land, it's just units. We'll find a nice value that works for us. But the idea is every time we have a frame happen, we need to have our acceleration. Acceleration is a constant, like it never changes, more or less, unless you like go really high up, get close to outer space. But for all intents and purposes, acceleration is a constant here on Earth. And it's velocity that's going to be changing now. All right, so every time we have a frame that happens in our program, we need to let the acceleration affect our velocity. And so we're going to change, first of all, this offset variable to velocity. That's what it really is representing. All right, so we're going to have a velocity variable. Once we start our ball, it has a velocity of 0. We just immediately drop it. It's not moving at all yet. But the acceleration is going to affect it. We're going to have a constant acceleration. Let's say it's, I don't know, negative 9.8 because we want to move it towards the ground initially. And so, like, the ball's not moving at all right here. Maybe a frame happens. The ball should be here. We have to have the acceleration affect velocity. So after a frame, the velocity becomes negative 9.8. All right? Every second, this should be changed by that amount. All right? Another frame or another second happens. We have the acceleration affect the velocity again. That's it's 19.6. And then ... onwards, forever and ever. It's going to be affected until it hits the ground, or like there's air resistance, things like that. Okay? So here's one frame. Then the next frame, it should be moving faster because it's already got that initial speed from the acceleration, and it's being affected even more now. And it keeps moving faster, right? That is the idea. So every time a frame happens, we need to let the acceleration affect our velocity. Are there any questions about the fancy words I've just said? I think it'll make a lot more sense once I program it, but we have to represent, in addition to velocity, which we're already representing in our offset variable, we have to also have acceleration now and have that change our velocity. All right, so let's take this program and copy it into a new file called, I don't know, bounce with gravity. And so the first thing I'm going to do is we notice that this variable, this offset variable, it's really the turtle's velocity. So let's change it. Everywhere we say turtle offset, let's call it turtle velocity. And it's -2, which means like we're moving by -2 in the negative y direction, right? We're moving by 2 in the negative y direction. That's the negative implies direction, right? So every time I see offset, it's going to be velocity instead. Boop. Boop. I think that was all of them. Let's search for it. Offset. It's just in the comments now. So instead of offset, velocity. Offset. to velocity. Change the velocity so that we move downwards. Okay, so I've just changed variable names. That's fine. It's still the same program. Nothing is new yet. But I'd like to now introduce acceleration. And it's not going to be like meters per second squared. The units now are going to have to be, because we draw a new frame, we update the turtle's position every frame. It's going to be like units per frame squared, essentially, right? Because the velocity of this ball is, it's moving 2 units every frame. It's units per frame. Therefore, the acceleration units must be units over frame squared, okay? So, first of all, when we drop the ball, it's initially not moving. So I need to change this initial velocity to 0, okay? That's the first step. So the initial velocity of the ball is 0. Unless we throw it or something. It's acceleration that's going to start bringing it downwards, all right? So turtle acceleration, and we want it to be accelerating towards the ground, so in the negative y direction. So it's got to be minus something. And I discovered in a previous semester that negative 1.5 is a good amount for the acceleration. All right, so the units for this acceleration variable are units over frame squared, units per frame squared, because every frame is when we're moving the turtle by some amount. Okay, so we're almost there. It's really like a couple line change. We just introduced this acceleration idea, and then the acceleration better affect the velocity every time we run it, every time we run our program. Okay, so let's see, how do I want to do this? Yeah, so in addition to the turtle's position being changed by its velocity needs to be changed by its acceleration. The acceleration must affect the velocity. So turtle, let's do that before we change its position, in fact, because the velocity is going to change anyway. So turtle velocity equals whatever it was before plus the acceleration. So the acceleration is going to change the velocity just like the velocity is changing the position of the turtle, the location of it. So turtle acceleration, that's the word. And so that's all I really need to do. So the acceleration affects the velocity of the turtle. And every time the turtle hits the wall, gravity doesn't flip, right? Gravity's always pulling us down, negative direction. Once the turtle hits the wall, it really is just the velocity that changes. So we don't have to change anything else. We've already essentially modeled the physics correctly. It's just we have to introduce gravity, introduce an acceleration. Gravity is constant. We never change acceleration. But the velocity of the ball can change. It'll bounce off. All right, so that's still fine. Acceleration affects the velocity. It's really, this is the only additional line we really need after we've introduced it. This is the only additional line, if I can spell additional line that we need to have gravity. So I cannot hype this up enough. This is going to look so cool. And it was really just introduce this variable, have it affect the velocity each frame. Everything else is the same as before. It's going to look so nice, assuming I didn't make any silly mistakes. But are we ready? Are you ready for a ball that drops and it looks like it's real life? Let's do it. Yay. I actually might need to change that velocity value. And it's like dribbling on the ground as it gets closer. That looked pretty nice. Let's play with the velocity value. I think my computer's got too many things open. So let's play with the acceleration value. Let's make it negative 2.5. I don't know. That'll pull it to the ground faster. Whee. Maybe that's a better animation. Yeah. Isn't that fun? Are there any questions about this? It was really just this variable, negative 1.0 maybe. Let's have it be pulled slower to the ground. I don't know. That actually looks a bit more like Earth. I like that better. So yeah, just have the velocity be affected by the acceleration, and we have a ball that bounces and eventually stops. Are there any questions about that? Does that seem too magical? Or does it make sense? I guess the one magical thing that's happening is like it's not immediately obvious why it's stopping. It's not immediately obvious why it's stopping eventually. Like, why does it lose speed on the way back up? We should be just making its speed go in the opposite direction. And the trick is, the reason the ball is eventually stopping, it's because of this inequality. If the turtle hit the wall and it tried to go a bit farther than the wall, we rein it back in to exactly hit the wall. And that messes with things. And that's eventually going to make it stop. So let's talk about that. So yeah, this inequality is essentially saying if turtle's y is less than or equal to negative 200 over turtle width over 2, like here's the wall, in our animation we might try to move the ball to here, right? And this is the bottom wall. And here's the top wall, essentially. In our animation, like right before we actually put the turtle anywhere, we might be trying to move the ball down here, and it's in between the walls, like it tried to move too fast. And so that's what this is discovering. Like it tried to go too far, or it hit exactly the wall. And what we do is we, instead of let it just bounce up from here, we move it back here, back up to here, and then we have it bounce up. Okay? So it wasn't able to get to its lowest point and bounce itself back up. All right? We can actually look at the speed of the ball. We can watch it be printed out each time, and that might help us. So, I don't know. Print current velocity, turtle velocity. Because the acceleration is always the same. And so here it is every frame printing stuff. And you can see that it's getting smaller and smaller. Like it was negative 26, now it gets to maximum 25. And so it is losing a little bit of energy each time it tried to go a little bit too far underneath the ground. And so what I'd like to do, I think, is let's find the speed of the ball right as it hits the bottommost point. Or, yeah, I think that would be perfect. What's the fastest this ball ever moves? Because we can shoot it back off at that same speed if we want to. So watch with your good eyes, everybody. Boop, right there. It looks like it was 26. We shot it back up with 26 velocity the first time. So potentially, and it's going to lose velocity every time it goes underneath the wall and we bring it back up because it didn't get to go as far as it really wanted to. If we just hard code every time it bounces off the wall, if we hard code the velocity to be, I don't know, that's only the bottom wall, by the way. It never even is touching the top wall at this point. If we hard code the velocity here, this is the bottom wall, right? Instead of this, if we just set turtle velocity to 33, it's 26.0, this will always shoot it back up with the 26 velocity, and so it'll never actually stop at this point. I should also stop printing this, because that'll make it run slower. So now every time it hits the bottom wall, I shoot it back off with the same velocity, 26. And so now it's always going to bounce up straight to the tippy top. and it'll never stop, but it'll still bounce like it's on Earth. So now it's going to bounce forever. Does that make sense? Like it was losing a little bit of energy because it tried to go underneath the wall, and we didn't let it go as far as it really wanted to go. But we could just hard code what it should have been. And that works just fine. And so we went from having a inelastic collision to a perfectly elastic collision. Always bounce upwards at, 26 units per frame off the wall. All right, so that's just an aside. If you change it back to how it was, it'll eventually stop for the reason I was saying. Are there any questions about any of that? Those are some weird, small technical details that maybe you don't care about, but they are the reason they did what they did, or the program did what it did. It makes for a fun answer, though, I think. Any questions about any of this? And so definitely play around with acceleration. I'm sure your screens, your computers can do it a lot faster, make it look a lot cooler. But yeah, play around with this program, make the ball giant, make the ball small, make it the way that you want it to be. Now you have all the pieces. All right, so the next thing that I want to do is we're not going to program this today. We're just going to come up with a game plan so that we can program it in our next programming lecture next week. But here is our new goal. I want to do that bouncing DVD logo thing from that Office episode. So if you've never experienced this idea, here is the Office episode. Let me mute it so that I don't lose my not Wikipedia, my YouTube channel. So I don't know, are we too young to know of DVD screensavers? But maybe we've at least seen this episode. But the little DVD thing in the background, it's moving across the wall in 2 dimensions instead of just 1. And they're trying to see if it hits the exact corner, which it will, and then they'll be very happy about it. But please watch this episode on your own time. It's very funny. But we're going to be programming this box moving around on a screen. All right, bouncing in 2 dimensions now instead of just 1. That's going to be our goal. All right. Sorry, I don't know which time it actually works in, so I'll have to stop us there. But here's what we were doing. We were bouncing like this. We'll go back to constant velocity. We were bouncing up and down just in one axis, just the y-axis. We are now going to change our circle to a square, of course, and then give it a random direction that is in any dimension. So 2-dimensional, bounce off that way. And then it's got to hit the wall, right? Hit the wall, boop. Hit the wall, boop. And just go off until the end of time, bouncing off just like this, as you would expect. Okay? And then maybe it'll even hit the corner for you. All right, so that is going to be our next program that we write. It's going to take a while to work up to it, so we're not going to program it today. We're just going to come up with the idea for how to program it. All right, but it's going to look really cool next time. All right, so here's the game plan. So as usual, we can keep a lot of the code that we have, right? We can keep the idea of drawing the window, the little screen boundaries. We can keep that square being drawn. That's perfect. We know how to put a circle in a certain spot. We can just change the turtle to a box instead. That's pretty easy. But we need to give the turtle a random starting location in the boundaries because it should be a different DVD logo animation every time, right? So once we run the program, the box could appear here at the start, or it could appear down here at the start, could appear anywhere. So we need to use randomness. Just like we were using to randomize the ball's the X position, the ball could have appeared up here or over here. It was always at the top wall, though. We're going to change that to be random in both dimensions. So maybe randomly the box chooses to start its life here. Right? So we're going to have to pick a random X coordinate and a random Y coordinate for this box, which is the turtle, right? And then we also want to give this box, the square, a random direction to start off in. Like it could be any of these, right? Any choice at the beginning, because it should be different every time. It should be random. Okay, so maybe we randomly choose that this is the direction that we start off in. And then once you've done that, you've chosen the starting position and the starting direction, you can start moving the box and bouncing off the wall. The rest is just move and bounce, move and bounce. Okay, that's the idea. So yeah, this is essentially the loop that we're going to be doing forever. Move in our current direction if there's nothing in the way, like maybe, I don't know, the direction is like this. The box should go here next. And then we should keep going in that direction, right? Eventually, we're going to hit the wall. And then we want to bounce off in the correct way, right? We were coming in this way, so we better like move off this way. And then we'll eventually hit the wall over here, right? And then we were coming in this way, so we better bounce off that way. There's some math to be done there. But we'll figure it out. And then the box should appear over here, right? So each frame, you just move it by its current direction, just in 2 dimensions now, and bounce off the wall if you need to, all right? So this is exactly the same as our bouncing ball that was just being changed a little bit up or a little bit down. It's now being changed a little bit left and right too, yeah? We now have a second axis. So if we hit any of the walls, left, right, top, or bottom, we have to bounce off, okay? So that's our game plan. And now the rest of this is going to be figuring out how we can represent this inside of a Python program. How can we figure out, like, I think it's pretty obvious to us at this point how to like start the box at a random location. X and Y value, just use the random library for that. But like, how do you represent a direction? A random direction in any angle inside of a program. So that's the next thing that we need to deal with and figure out. Okay? So here's the idea. Lower level game plan. So we'll make the turtle the square, of course, right? And we could use the coordinates of that turtle to move him around. That's fine. That's all from before. So again, turtle is now the square. He has an X and Y coordinate that we can deal with. We can move his center. And surprisingly, you can actually store the direction of the turtle, even if it's 2-dimensional, using offsets. All right? It's just that this time we're going to have 2 offsets. All right? One for the X and one for the Y. And here's the idea. Like, regardless of what the direction is of the turtle, let's say just for fun, without loss of generality is the mathematical term, let's say that the turtle's direction was over here. Like the next frame, he should be over here. Like this should be the turtle's new position after 1 frame, right? So how do we get the turtle there is the question. The turtle should be moving in that direction. The new box better appear right here, right? How can we represent that inside of a program? Let me draw that in the middle. That doesn't look as nice. That's about as good as I can get it. How can we represent that in a program? And the answer is, well, how do we get a box from here to here? It's just, you can think of it as an axis at a time. You can move it this way a little bit, right? To move the box to this position. You can move it to the right a little bit and then move it up a little bit. Does that make sense? And so now it's like a right angle. There is a certain change in your X direction, and then there's also a certain change in your Y direction. And that will get you anywhere. Does that make any sense? So like, you pick a random direction, it's really just an X and a Y offset. If you want to move the turtle up here, it's just go over and then go up. If you want to move the turtle over here, it's just go left and go up, right? We've broken this down to single axis movements. Go right, go up. Go left, go up. If you're going this way, go left, go down. If you're going this way, go left, go down. All right? If you're going in any of these directions, you can just go straight up, go straight down, go straight left, go straight right. That's fine. There's 0 Y offset or 0 X offset. But if there's something in between, you just go a little bit in one axis, go a little bit in the other. There's a change in X and also a change in Y, and that can represent any direction that you want to move in. Okay? That's the idea. So yeah, each frame you want to move the turtle's x-coordinate and y-coordinate by that amount that's stored in our direction. And every direction has an offset. It's an x offset plus a y offset. Okay? And so this is, again, by offset we mean velocity. That's how it's going to move. That's how fast it's going to move. If it's a bigger direction. It's like, these are the same direction, right? But one will have a faster velocity. These two arrows, right? It's the same direction. Move a little bit in the x direction, a little bit in the y direction. And this one's like move a little bit more in the x direction, move a little bit more in the y direction. But they're both going to be the same place, the same angle. Just this one will get you there faster. Does that make sense? So with an example, let's pretend our turtle randomly starts here at this location. Let's pretend this random location for our turtle is the coordinate 1, 1. We got lucky. And then let's pretend that our direction is, our change in x is 3, and our change in y is 2. That's what we randomly picked, right? So every time we move our box, we look at where it is now, and we change its x by that amount, by delta x, and we change its y by that other amount, by delta y. Okay? So the next coordinate for this box, it started at 1, 1. The next coordinate is going to be 1 plus change in x and 1 plus change in y. And that's going to give us animation and movement. So the next place that this box is going to go is 4, 3. 4, 3. All right, so move over by 3, 1, 2, 3, up by 2. That's your direction, essentially. And this is the new place that the box will go. So now the box is at 4, 3. And if the box moves again the next frame, we're still moving in the same direction if we don't hit a wall. We again go over 3 and up 2. And this is the new location of our box. It's going to be what? 4 plus 3 is 7. Oops. I want to use dotted lines, I guess. 4 plus 3 is 7. 3 plus 2 is 5. So this is now at 7, 5. All right? And so that's how you can represent direction inside of a computer. Just an x offset and a y offset. This is like go over by 3, up by 2. Go over by 3, up by 2 each time. And that moves to the upper right direction. Okay? And anywhere in between if you pick different offsets. Are there any questions about that? Does that make enough sense? So before we just had a single offset. Just go change the y by this amount, change the y by this other amount. Now we'll have a second axis. Change the x by this amount and also change the y by this amount. And that will give us arbitrary two-dimensional directions. And then after that, all that we have to worry about is hitting a wall. So we have to figure out how to check whether we hit a wall, and then also we have to bounce off the wall in the correct way, right? Because if the box was going, if it was coming in this way, it needs to bounce off in that exact way. And that's based on the previous direction. So there's a calculation we have to do to get the new direction. All right, so that's the next thing that we have to figure out. So let's figure that out. So again, let's keep the current sizes that we were using. Like the wall was over here, negative 200, positive 200. This is what it looked like. Let's see. Here is our bounding box. I'll do my best to draw it. There we go. And so this was 0, 0. And over here was like negative 200, positive 200. That was our bounding box that we drew. And so this is width 400. This is height 400, etc., etc. This is the line y equals negative 200. This is the line y equals positive 200. And this is going to tell us when we hit the wall, right? That's why I'm drawing all this. And we also have to worry about hitting the left wall. So what is this wall in terms of like coordinates? It's x equals negative 200. This is x equals positive 200, this wall right here. Does that make sense? And we need to check for these special numbers, and that'll tell us if we hit the wall, okay? Because if the box is moving this way, We need to stop it once it gets right here, right? That's what we need to do. So how do we notice if that box is hitting the wall? Or if it's just touching it as well? So here is the idea. So, for example, the turtle is going to hit the left wall when its x-coordinate, essentially, you can think of it this way, but it's really the center, when that x-coordinate is less than or equal to negative 200, right? Here's the x equals negative 200 line. If the box ever reaches that or tries to pass it, we've hit the wall. Are there any questions about that? Does that make sense? If the x value of the box, wherever it is, it could be up here, it could be down here. If it's ever if it's ever equal to negative 200 or it's past it, it's great, or it's less than that, we have hit the wall. We need to bounce off. Same for the right wall. It's just positive 200. If we've ever got an x value that's greater than 200 or exactly like equal to it, we've hit the right wall. Same for up and down. If the y is equal to 200, if the y is less than or equal to negative 200, we've hit the top and the bottom wall. Okay, so that's how we'll check for all that. And now we have to worry about how do we bounce off. And also remember that you can hit both at once, like that's the Office episode. Do you check for that? How do you figure that out? That's another question. Okay, so the trick is going to be, let's pretend like the box is moving this way with a certain delta x and a certain delta y. If we, for example, hit the top wall, let's try and derive what needs to happen, how it needs to bounce off. Because let's say the box is here, it's coming this way, right? It needs to bounce off in what direction? It's not this direction, it's not this direction, it's exactly this direction, right? That's how it should be bouncing off. So what is that arrow? How do you represent that as the direction that we know how to represent? Like it's that direction. It's a certain x and y, right? It's a certain delta x and delta y. What's similar and what's different? I think I drew it slightly off. It's got to be like a 90-degree angle where they meet. But does anybody see the similarity between the original arrow and the new arrow? What's the same and what's different? It's like you took this arrow and you kind of flipped it a little bit, right? You like put it in a mirror. What does that mean? So, for example, delta x, now go away zoom window. All right, you're not going away. Oh, there you go. Delta x, for example, it's still going that way. Delta x is still that way. Go this way a little bit, and then go up a little bit. Delta x, for this new direction, even though it's inverted, it's still going that same amount. Delta x is still the same for that new direction that we're bouncing off in. It's just, instead of going up after going to the right, we're going right and then we're going down. We're going down first, kind of. Okay? But it's the same amount. This amount here is the same as the amount from the original direction. Does that make sense? So it's delta y again, but it's negated. All right? Because the delta y originally from the first direction was going up. The new delta y from the bounced direction is going down, so we have to negate it. That's the trick. Any questions about that? That's really technical. And we'll program this next time. It'll make more sense, I promise. But that's the idea. That's how you determine what the new direction is after you bounce off the wall. Let's try it for the side now. Let's say we were coming in this way. We hit the wall. Here we are hitting the wall. Then we want to bounce off that way, right? So this is move over by a certain amount. Let me draw this bigger. This was move over this way. Here's our box. And move off in that direction. So here is our x and y. So move that way and then move up. Versus the new direction is going to be move right, then move up. So notice what's the same? The delta y. The delta y for this bounce off the side is the same. What's different is we were coming in it to the left in the negative x direction. This was our original delta x. But we need to bounce off going to the right in the positive x direction. So we need to negate our x offset. And that'll give us our new direction. Are there any questions about that? So that if we hit the top wall, we need to negate our y offset. And if we hit a side wall, we need to negate our x offset to bounce off in the correct way. That's going to be the trick. So to hopefully drive home the idea behind this, let me give us a very, very worked out example with real numbers. Okay? So let's say we're about to hit this sidewall. Let's say that here's our box, and here is its coordinate. Like this box right now is at negative 198 and 2 or something. And let's say the current direction of this box, the place that it's going to move to, the current direction of the box is negative 2 over and then positive 3 up. So here's the direction of the box. Just like this. Let me try to make a bold line here. And so after a frame, for example, the box is going to move from here to go over 2. Oh, sorry, it's minus 2, minus the x direction. The box is going to appear, let's say right here. It's going to hit the wall. I'm trying my best to draw this well. So it's minus 2 and then up 3, right? Minus 2, up 3. And so the new place that the box is going to be at is exactly negative 200 and then it's positive 5. So that's how it's moving. And now we need to bounce it off the wall. And given what we said, right, it needs to bounce off this way. That's the correct direction, which is going to be not go to the left 2, but go to the right 2. Yeah? That makes sense? Go to the right 2, then go up 3. This is 3, this is 2. And so the new direction has got to be this way, which is go to the right 2, and then up 3. That's how it needs to change when you hit the sidewall. And so, didn't quite draw this to scale. It should be like parallel with this other box, but the new location, at least, the exact location of this box should be negative 198, and then it's 5 plus 3, so 8. Does that help using actual numbers? Do we see how this is the initial direction? It's got to bounce off the wall this way, and the offsets that create that new direction are you take what you had for the y, and then you negate the x offset. And that will bounce you off in the correct new direction. Any questions about any of that? Does that make enough sense? I will program it next time, and the fruits of this labor will become apparent, and it will look very cool, but I want to make sure we're all on the same page before we do it. That's why there's a lecture in between. This was just the planning stage. But now, it's not going to be too hard. We're going to have a few extra variables. We're going to have the turtle's x and the turtle's y, which we were keeping track of. And then in addition to the y offset of the turtle, we have to also store an x offset, because that'll give us direction. And then instead of, or in addition to, bouncing off the top and the bottom wall, we have to also bounce off the left and right walls. And the way that you bounce off is going to involve negating one of the offsets, either the x offset or the y offset. Okay? That's going to do it. That will be the idea there. Any questions? Was that just too much math, maybe? That's what you got to do if you want to write programs that are like interactive with games. You have to do a lot of math. Now you know. All right, so the last thing that I want to do today is introduce your next programming assignment. This will be programming assignment 8. This will be due week 16, so the week before the last week of classes. And here is your assignment. You'll take not what I wrote today, but the bounce program that I wrote last time. And so here's essentially what I want you to do. Here's the program that you're going to be writing. every time the ball bounces on the wall, or let me reload it because it's supposed to start as a ball. Every time the ball, oh no, because it's a GIF, it just always starts in the middle, darn. Every time the ball bounces off a wall, a weird thing should happen. That's going to be your program. So every time you hit a wall, you'll take the program that I wrote, not this programming lecture, but the one before, copy and paste it, and then you're going to make it do a weird thing every time it bounces off the wall. Change the size, change the color, change the speed. That's what's happening if you can't see it. Change the shape of the turtle from a square to a circle to a turtle. And so this is essentially what it's going to look like when you run yours. Okay? So that's going to be what you're going to write. And let me show you your requirements. Oh, here's how it starts. It looks normal when it starts, but then it bounces off a wall and like changes its shape. It's all random. And now it changes its speed, changes its color again randomly, changes its speed one more time, changes its shape, changes its X offset. I think that's a good amount. All right, so your job will be just like that program that I made. Use the turtle, use the random modules to do the following. So you're going to make that bounding square to represent the walls. You're going to make that ball bounce up and down. So we've already done that, right? That's just the program from last time. You'll copy and paste it. And then the new thing that I want you to add is every time the ball hits the wall, or maybe it's not a ball anymore, randomly make something weird happen, all right? Every time the ball hits one of the walls. So randomly pick some of these options. You have to do, I think, at least 3 different weird things chosen randomly every time the ball hits the wall. But you just pick one out of the 3 that you've made, for example. So here are some potential things that are weird that you could do, like change the color of the ball to be something random. Change the size of the ball to be something different, like change it to be 0.25 stretched. Change it to be 4 times the stretch amount. Okay? If you want a random decimal number, you need to use random.uniform. Okay? I guess I should put like 0.25 and 4 in between, but I think you get the idea. Another weird thing that you can do is like change the X coordinate of the ball to be a random one within like the screen, so like it's teleporting. Change the speed by a random factor. That will involve changing the offset. And then you could randomly change the shape of the turtle to do something, to be like a square, an actual turtle. But those are the things that you want to do every time the ball hits one of the walls. Randomly pick one of these weird things to do and do it. Okay, that's the bulk of your assignment. But I want to force you to use functions. All right, so you must make a new function called like I just hit the wall or do something weird, something like that. You have to make a function and call it. Okay, every time your ball hits the wall, and that's the function that's going to actually perform that random thing. It'll pick the weird thing to do and do it. Okay, so you'll call that every time your ball hits the wall. That'll be inside of those if statements that check, did I just hit the wall? Did I just hit the wall, right? So your program must have at least 3 different weird things. So you can choose from this list, you can pick some of your own, but at least 3. So every time the ball hits the wall, it like flips a 3-sided coin, and it's like, all right, I'm going to do random thing number 1. I'm going to do random thing number 2 this time. Okay? But that is the idea, and it should end up looking something like this. I did all of those options in this example, but that's kind of how it's going to work. Are there any questions about that? So you'll take pretty much what I had. You'll write a function with a nice name, and every time the ball hits the wall, you'll call that function, and it'll do something weird to the turtle. Affect its speed, affect its size, affect its shape, color. But you got to use a function to do it, and it has to only happen every time you hit the wall. Okay? Use the documentation pages to make your program, and I think that is everything that I wanted to say. So try to get it cooler than my example if you'd like, if you want a challenge. But that is the idea. So your ball is bouncing. Every time it hits a wall, it does something magic and random, involving a function, though. It's the function that chooses the random thing and does the random thing. Okay? Any questions about any of that? That'll be due week 16, which is apparently the 26th. Oh, and here's a hint for like how to pick one of the random things to choose from. let's say that you have 5 different random things that you've chosen to implement. Here's how you choose which of those things to do every time you hit the wall randomly. You can do it like this. You can pick a random number from 1 to 5. There's a random function for that, right? Let's say you have 5 weird things to choose from. You can pick a random number between 1 and 5 and just assign to each number one of those random things. Set that to a variable called n or something, and then just use a big long if-elif statement to check that n variable that got set to some random number. And it's like, all right, if it ended up being 1, do that first weird thing. If it was 2, do that second weird thing. That's how you can choose from your 5 weird things, for example. Just pick a random number and check it. Okay, so that's a hint if you're having trouble. But that should be everything that I wanted to say. Are we good with that? So you got a while to do it and make it look cute. You can introduce gravity if you'd like. And I believe that is officially everything that I wanted to say. So the rest of the time is yours to work.